Somewhere in a lab in Santa Barbara, California, a chip with 105 qubits completed a computation in under 5 minutes. The fastest supercomputer in the world, a machine that fills a building, consumes 21 megawatts of power, and costs $600 million, would need 10 septillion years to do the same thing. 10 septillion. That's a 1, followed by 25 zeros. It is, to put it in perspective, roughly 10 times longer than the current age of the universe, calculated across multiple universes, and the number still doesn't get there. That result was Google's opening announcement for its Willow chip, published in Nature in December 2024. It was extraordinary, and if it had been the whole story, you could reasonably argue about whether it was practically meaningful. A benchmark designed to show maximum quantum complexity is not the same thing as solving a useful problem. Critics said as much, loudly, and they weren't entirely wrong. Then, October 2020 happened. Google announced what it called the first ever verifiable quantum advantage on hardware, an algorithm called quantum echoes that ran 13,000 times faster on Willow than the best classical algorithm on one of the world's fastest supercomputers, and produced results that could be independently repeated and verified. That's not a synthetic stress test. That's a quantum computer solving a problem with genuine scientific relevance, faster than classical computing can follow, and it's a different kind of claim than anything that came before it. Today we're doing something we haven't done in this series yet. We're leaving Windows behind entirely. Quantum computing doesn't run on Windows 11. It doesn't have a start menu or a forced Microsoft account. It runs on qubits cooled to temperatures colder than outer space, and it is, right now, in the middle of the most consequential hardware race of the decade. Let's track the pulse. Before the benchmark numbers, before the quantum echoes algorithm, before any of the competitive context, you need one concept. Everything else in this story flows from it. Classical computers store information as bits. A bit is either a 0 or a 1, full stop. Quantum computers store information as qubits, which can be 0, 1, or a superposition of both simultaneously. A property that allows quantum computers to explore many possible solutions at once, rather than testing them sequentially. That's the theoretical power. The practical problem is that qubits are extraordinarily fragile. They lose their quantum state, a process called decoherence, when they interact with almost anything in their environment: heat, vibration, stray electromagnetic fields. Errors accumulate. At a certain scale, the errors multiply faster than you can use the computation for anything useful. Quantum error correction is the field that tries to fix this. The basic approach is to encode one logical qubit, the qubit actually doing useful computation, across many physical qubits working together, so errors can be detected and corrected without disturbing the quantum state itself. The problem that stumped the field for nearly 30 years is that as you added more physical qubits to correct errors, you introduced more qubits that could themselves fail, and the error rate tended to go up, not down. Adding qubits was supposed to make the system more reliable. In practice, it kept making it worse. This was the defining existential barrier to scaling quantum computers to any size that could do genuinely useful work. Willow broke it. In December 2024, Google demonstrated what is called below-threshold quantum error correction, as they scaled from a code distance of 3 to 5 to 7, meaning increasing the number of physical qubits used to protect each logical qubit. The error rate halved each time rather than growing. Exponential error reduction, going in the right direction for the first time in 30 years of trying. Hartmut Neven, founder and lead of Google Quantum AI, described the field's reaction simply: the whole community breathed a sigh of relief. Not because the problem was solved. The logical error rates Willow achieves are still orders of magnitude too high for the large-scale fault-tolerant algorithms that would crack encryption or fully simulate drug molecules. But because the proof is now in hand that quantum error correction actually works at scale, in practice, on real hardware, not just in theory, the scaling pathway is confirmed to be physically real. That is a fundamentally different situation than the field was in 2 years ago. Willow itself is a 105-qubit superconducting chip manufactured at Google's own fabrication facility at the University of California, Santa Barbara. Its qubits are transmon-type superconducting circuits, macroscopic quantum devices that behave like artificial atoms when cooled to temperatures near absolute zero. Across its full 105-qubit array, Willow achieves fidelities of 99.97% for single-qubit operations, 99.88% for 2-qubit entangling gates, and 99.5% for qubit readout, all operating at speeds of tens to hundreds of nanoseconds per operation. Julian Kelly, director of quantum hardware, described it simply: think of Willow as everything good about the previous Sycamore generation, with better qubits and more of them. Let's address the number that made every headline in December 2024 directly, because it attracted two kinds of reaction: awe and skepticism, and both were reasonable. The benchmark Google used is called random circuit sampling, or RCS. It is specifically designed to be the hardest possible task for a classical computer to simulate, while remaining achievable on a quantum chip. You can think of it as a stress test designed from the ground up to create the widest possible performance gap between quantum and classical hardware. Willow's performance was astonishing. It completed this computation in under 5 minutes, a task that would take one of today's fastest supercomputers 10 septillion years. To give that number its proper context, 10 septillion years is 1,025 years. The current age of the universe is approximately 13.8 billion years, which is about 1.38 aspects 1010 years. The Willow benchmark result is larger than the age of the universe by a factor of roughly 10 quadrillion. Classical computing cannot close that gap by building faster supercomputers. The gap scales at what Google's team described as a double exponential rate as the quantum system improves, meaning the harder the benchmark gets for classical hardware, the faster it gets on quantum hardware. Some physicists found this result philosophically destabilizing in a way that goes beyond the hardware story. The reason Willow can do this is that quantum computing explores solutions by leveraging quantum superposition and entanglement across a state space that, for a 105-qubit system, contains 2,105 simultaneous possibilities. A number so large, it has no physical analog in classical computing. One interpretation, championed by some quantum physicists, is that the computation is effectively being distributed across multiple parallel branches of reality simultaneously, a framing that maps uncomfortably onto the many worlds interpretation of quantum mechanics. Google's own team was careful not to make that claim publicly, but the question circulated widely enough that it became its own story. The legitimate skepticism came from a different direction. RCS is contrived. It's designed to be hard for classical computers, not to solve any real problem a human cares about. IBM and other researchers pointed out, correctly, that classical simulations of RCS had improved substantially since Google's 2019 Sycamore benchmark, narrowing the claimed advantage from its original framing. The 1025-year figure is real for 2024's classical hardware, but this specific benchmark is hard to simulate classically, is not the same as quantum computers are now useful for practical problems. That distinction matters enormously, and Google knew it, which is why the second announcement 10 months later was structured the way it was. October 22nd, 2025. Google's second major Willow announcement landed in Nature, and the framing was deliberately different from December 2024. This was the first time in history that a quantum computer successfully ran a verifiable algorithm on hardware, surpassing even the fastest classical supercomputers, 13,000 times faster, and computing the structure of a molecule. The algorithm is called quantum echoes, and it works by probing the chaotic internal dynamics of quantum systems using what are technically called out-of-time order correlators. Measurements of how a disturbance in one qubit spreads across the entire chip over time. The technique uses a 4-step process. Run quantum operations forward, perturb a single qubit, reverse the operations, and measure the resulting echo. Constructive quantum interference amplifies the signal. The result is a highly sensitive measurement of how information propagates through a quantum system. Information that is directly useful for understanding molecule structure, magnetic materials, and at the extreme theoretical end, the dynamics of black holes. In collaboration with the University of California, Berkeley, Google ran the quantum echoes algorithm on 2 molecules, one with 15 atoms and another with 28 atoms. The quantum results matched those of traditional nuclear magnetic resonance measurements, the gold standard technique for determining molecular structure, and in some cases revealed structural information that NMR couldn't access at all. Certain data points that Willow generated in seconds would have taken an estimated 3 or more years each to simulate on the Frontier supercomputer, one of the world's fastest. The verifiable part of the claim is doing specific, critical work. In the 2019 Sycamore benchmark, the results could be spot-checked but not fully independently verified. There was no way to confirm them except by running the same quantum circuit on the same or similar hardware. Quantum echoes is different because the results can be compared against physical reality. Run the same molecule structure question on NMR, get the same answer, and you've independently confirmed the quantum computation without needing another quantum computer. That closes the most significant methodological criticism that had followed quantum advantage claims since 2019. The key result is that Willow produced measurable quantum signals that no existing classical supercomputer can feasibly simulate, demonstrating a computation beyond classical reach. The scope is still narrow. This is a specialized measurement technique applied to specific small molecules, not a general purpose computational breakthrough. But the direction of travel is unmistakable, from synthetic benchmarks to physically Meaningful measurements, from unverifiable to independently verifiable results, from tens of minutes to seconds for computations, classical hardware can't follow. Every credible analysis of Willow's results carries the same honest caveat, and we're going to give it the space it deserves rather than burying it in a single sentence. The most common public worry about quantum computing is cryptography, that a sufficiently powerful quantum computer could run Shor's algorithm and break the RSA, encryption protecting banking transactions, government communications, and essentially all internet security. This fear is legitimate on a long enough timeline. It is not warranted today, and it won't be warranted for a long time after today. Breaking 2048-bit RSA encryption with Shor's algorithm would require millions of logical qubits operating with error rates far below what Willow achieves. Google's own team stated they are at least 10 years out from breaking RSA. Willow has 105 physical qubits. The logical error rates reported, around 0.14% per quantum cycle, remain orders of magnitude above the roughly 10 to 6 error rates believed necessary for running the large-scale fault-tolerant algorithms that could threaten encryption. To reach fault-tolerant scale, estimates range from 1 million to 10 million physical qubits with dramatically improved error rates, operating in a system architecture that doesn't yet exist. Post-quantum cryptographic standards, encryption algorithms designed to resist attacks from both classical and quantum. Computers are already being standardized and deployed. The transition is underway long before any cryptographically relevant quantum computer exists. The second honest limitation is scope. Quantum echoes is a genuine scientific result, but it is a specialized physics measurement technique, not a general-purpose computation. The molecules tested were small, 15 and 28 atoms. Pharmaceutical drug discovery, materials science simulation, and quantum chemistry at scales relevant to real-world applications will require fault-tolerant quantum computers with millions of logical qubits and error rates Willow doesn't approach. Google's roadmap targets a milestone 6 machine somewhere around the end of the decade. Practical, broad utility is a late 2020s to 2030 story, not a 2025 story. What Willow has actually done, and this is substantial even with those caveats in place, is prove the physical pathway. Below, threshold error correction works. Verifiable quantum advantage over classical supercomputers on a physically meaningful problem is real. The scaling trajectory is confirmed. Those were the 3 contested questions in quantum computing for the better part of a decade. All 3 now have positive answers. That changes what researchers, investors, and policymakers can assume about the eventual destination, even if the timeline remains genuinely uncertain. Google doesn't own this field, and the Willow story only makes full sense alongside what the rest of the industry is doing simultaneously. IBM is the largest player by user base and developer ecosystem. Its Qiskit software platform has more users than any competitor in quantum computing. On hardware, IBM's Flamingo multi-chip system reached 1,886 qubits in 2024. Its scaling strategy is explicitly different from Google's. IBM is prioritizing accessibility and volume, making quantum computers available to researchers and enterprise customers through cloud access today, even before full fault tolerance. IBM's own roadmap targets systems with 1,000 or more qubits with surface code error correction by 2027, aiming for logical error rates in the range of 1010. The approaches are not in direct competition so much as they reflect different philosophies about how to get to useful scale. Google is prioritizing error correction quality with fewer qubits. IBM is prioritizing qubit count with a larger developer ecosystem underneath it. Microsoft is pursuing the highest risk, highest potential reward path in the entire field. Rather than building better superconducting qubits, the approach Google, IBM, and most of the industry use, Microsoft is betting on topological qubits, which store quantum information in the topology of a quantum state itself rather than in the state of a specific physical particle. The theoretical advantage is that topological qubits are inherently more resistant to the decoherence errors that plague conventional quantum hardware, without requiring the same external error correction overhead. The practical problem is that building them is extraordinarily hard. Microsoft unveiled Majorana 1 in February 2025, the world's first quantum processor based on topological qubits, claiming the architecture is theoretically scalable to 1 million qubits on a single chip, a number that would leapfrog the superconducting approaches if it holds. Majorana 1 attracted significant scrutiny from physicists over the evidence for the underlying quantum states it relies on. Microsoft's June 2026 follow-up, Majorana 2, replaced aluminum with lead in the superconducting material stack, more than doubling the topological protection gap and improving parity lifetimes by more than 1,000-fold, from milliseconds to over 20 seconds. That's a meaningful engineering advance, though the path to a fault-tolerant topological machine remains genuinely uncertain in a way that Google's superconducting roadmap currently is not. Microsoft's approach remains the longest shot in the field, and the one that could produce the most dramatic outcome if it works. IonQ represents a third hardware philosophy, trapped ion quantum computers, which hold individual ionized atoms in place using electromagnetic fields and manipulate them with lasers. Trapped ion systems have coherence times roughly 100 times longer than superconducting alternatives, meaning each qubit stays in its quantum state long enough to do more operations before decohering. IonQ reached 64 qubits in 2026, up from 32 in 2024. The trade-off is speed. Trapped ion gates are slower than superconducting gates, which limits how many operations can be performed in the available coherence window. IonQ's revenue doubled year over year, suggesting enterprise interest in the approach even at current scales. Quantinuum, the quantum computing joint venture formed from Honeywell's hardware unit and Cambridge Quantum, produced one of the most cited results in the field through a collaboration with Microsoft. 12 logical qubits encoded with a 2 in 1,000 error rate, among the lowest ever. Reported for logical qubits. D-Wave, the longest-running quantum computing company, operates differently from all of these. Its systems are quantum annealers rather than universal gate-based machines, designed to solve optimization problems by letting a quantum system settle into its lowest energy state. Its Advantage 2 system went generally available in May 2025 with over 4,400 qubits, accessible both through cloud services and as an on-premises machine. The broader investment context reflects how seriously the field is being taken. The quantum computing industry raised nearly $4 billion in the first 3 quarters of 2025 alone, triple the total for all of 2024. Quantum error correction research produced 120 peer-reviewed papers in the first 10 months of 2025, up from 36 in all of 2024. This channel covers hardware. Quantum computing hardware is exotic by the standards of what we usually discuss. There's no PCIe slot for a qubit array, and your workstation isn't going to boot off a quantum drive in this decade. But the implications for people who build and work with computing hardware are real, and it's worth being concrete about them. The materials, science and drug discovery applications being demonstrated on Willow, are directly upstream of physical hardware. Semiconductor development requires understanding quantum mechanical behavior at the atomic level, behavior that classical simulation struggles to model accurately for complex materials. A quantum computer that can accurately simulate molecular structures and electron dynamics is a tool that could accelerate the development of new transistor materials, battery chemistries, and semiconductor processes that classical computers cannot fully explore. TSMC, Intel, and Samsung are watching this field not as bystanders, but as potential end users of the technology. Energy grid optimization, supply chain logistics, and financial modeling are the other near-term application areas most often cited by quantum computing companies for practical value before full fault tolerance. These are optimization problems, finding the best solution among an enormous number of possibilities, where quantum algorithms can theoretically provide substantial speedups over classical methods, even with current noise levels, using a class of approaches called variational quantum algorithms that are designed to work within the error budgets of near-term hardware. The encryption story, as we covered, is a longer timeline, but it's one that hardware and security professionals need to be watching actively rather than reactively. Post-quantum cryptographic migration is a multi-year infrastructure project. The fact that a cryptographically relevant quantum computer is still a decade or more away does not mean the migration work should wait a decade. The U.S. National Institute of Standards and Technology finalized its first post-quantum cryptographic standards in 2024. Implementation is already underway in government and financial systems. If you're responsible for any infrastructure that handles long-lived sensitive data, the relevant question isn't when will quantum computers break RSA? It's how long does it take to migrate, and when does that clock start? So what did Google actually admit? Not that classical computing is dead, not that encryption is broken, not that we're on the eve of a quantum revolution that changes everything next Tuesday. What Google demonstrated across 3 announcements spanning December 2024 through April 2026 is something more specific and more durable than any of those headlines. First, the 30-year barrier to quantum error correction, the problem that kept quantum computers from scaling to useful sizes, is broken in practice on real hardware. Second, a quantum computer has now solved a physically meaningful scientific problem faster than any classical supercomputer can verify, and had those results confirmed independently against experimental data. Third, that result was obtained on hardware running with the kind of gate fidelities and coherence characteristics that map to a credible scaling roadmap for the rest of the decade. Willow's stability is the key to running quantum machine learning algorithms that can handle optimization problems and massive datasets far beyond the reach of classical AI. The destination is still years away. The route, for the first time, has proof behind it rather than just theory. What changed on April 7, 2026 is subtle but significant. Quantum computing stopped being a field where the fundamental question, can this actually work at scale, was still genuinely open. The answer is now confirmed as yes. What remains open is how long it takes, how much it costs, who gets there first, and what problems get solved in what order once they do. Those are different questions, and they're harder to answer, but they're better questions to be asking than the ones that dominated the field 3 years ago. We'll be tracking this story as the milestones arrive. If you want the next hardware report the moment it drops, hit subscribe and turn on notifications, and tell us in the Google comments whether you think Google's roadmap to end-of-decade fault tolerance is realistic, or whether Microsoft's topological qubit bet is the one that changes the race. We'll see you in the next one.